So Chapter 5 is all about states of matter, gases, liquids, and solids. Now we're not going to go through the entire chapter, so if you're following along in your book at all, make sure that you are looking at what sections we're covering from the calendar, because we're mainly just focusing on the gases. So with gases, we need to talk about pressure, because gases exert a certain amount of pressure. So what pressure is a force exerted by the gas molecules as they collide with the surfaces around them. So in this diagram here, those gold spheres, are actually molecules, gas molecules. And to figure out the pressure of that gas in that container, we can actually calculate it because those molecules are applying a certain force on the inside walls of those containers. So the more often they collide with the container, the walls of the container, the higher the pressure is going to be. So the more molecules you have and the smaller area they're confined in is going to determine the pressure. So when we calculate pressure, we take the force applied, so the force those gas molecules are applying, and divide it by the area that they are in. Okay, so the higher the force, the higher the pressure. The smaller the area, so the smaller the container, the higher the pressure as well. When we look at units for pressure, it can be measured in several different units. We have ATM, atmospheres. We have PA, pascals. We also have millimeters of mercury and torr. So there's different units for pressure, and these are used for various different reasons. Okay, so it depends upon what type of pressure you're talking about. If you're talking about atmospheric pressure, barometer, weather, different units can be used. So here are just some conversion factors, since there are so many different units for pressure, to convert between millimeters of mercury and torr, or between ATM and pascals. So let's look at some of the equations for Chapter 5. So Chapter 5 is going to be a lot of different gas equations, gas laws, and solving for pressure, volume, temperature, even moles. So we're going to start by talking about Boyle's law. So the first of the equations. So for Boyle's law, we have the equation PI VI is equal to PF VF. So what do those variables mean? P sub I is the initial pressure. And when we're using this equation, our initial pressure is going to be in ATM. VI is for initial volume, and that is going to be measured in liters. So this is the initial pressure and volume of that gas. Oftentimes you'll see this equation with a P1V1 instead of PIVI. It means the same thing. The other side of the equation, we then have our final pressure and our final volume. When we're applying Boyle's law, it's under constant temperature. So whenever I say a variable is constant, what that means is that variable is not needed in the calculation. So since the temperature is constant, we don't need temperature in that equation. For this equation, for Boyle's law, pressure and volume are inversely proportional. Okay, so when I say inversely proportional, what that means is if one goes up, the other is going to go down. Okay, so if the pressure goes up, the volume is going to go down, and that's what I have shown in this diagram over here. So in the bottom picture, my pressure is low, right? I just have one weight on that gas. So low pressure, so that means pressure is down. So let's look at the volume. The volume of the gas is going up. So low pressure, high volume. They're going in opposite directions. Now, let's say I increase the pressure. So in this second diagram here, I added another weight, making the pressure now go up. So since the pressure went up, what happened to the volume? It went down because they go opposite directions. They're inversely proportional. Pressure goes up, volume goes down. Pressure goes down, the volume then is going to go up. So utilizing Boyle's law. So here is a word problem using Boyle's law. Now we're going to have a lot of different equations, so you're going to have to use clues in the word problems to figure out which equation needs to be used, because the word problem itself isn't going to say use Boyle's law to solve. So a sample of oxygen occupying a volume of 5 liters at 150 atm. Okay, so how I like to approach these problems is I like to look at all the information given, look at the units present, and then convert if necessary. Okay, so I have liters and I have ATM. Those are the units I want, so I don't need to convert anything. My next step then is to make a list of knowns and unknowns. So that's what this is down here. So that 1.50 atm, that's a pressure. So I label that as my P1, my initial pressure. That 1.5 atm is referring to this 5 liters of volume. So that 5 liters is going to be my V1, my VI, my initial volume. So I have my initial pressure, my initial volume. The question's then asking me what pressure needs to be applied if I want to compress that gas down. So it's saying my final volume I want to be 1.5 liters. So at that 1.5 liters, what is my final pressure? So I put a question mark by P sub F because that's what I'm trying to solve for. Looking at these variables, I check my equations and see what equation will work. In this case, Boyle's law is going to work because it has all the variables I need. It's got a PI, a VI, a PF, and a VF. So with all these equations, you're going to be given all but one variable. And that you're going to have to rearrange the equation to solve for the variable that they're asking you to solve for. So now let's use that relationship between volume and pressure in Boyle's law and predict what the final pressure is going to be. So we said that volume and pressure are inversely proportional. That means if one goes up, the other goes down. One goes down, the other goes up, right? So what's happening here? So we have an initial volume of 5 liters. The final volume is 1.5 liters. So what's happening to the volume? Is it going up or down? It's going down. Okay, so if the volume's going down, what's going to happen to the pressure? We would expect the pressure to go the opposite direction since they're inversely proportional. So the pressure should be going up. So when I solve for my P sub F, I should get a higher number than 1.5 because my pressure should be increasing. So what I did here was plug in the numbers, 1.5 for PI, 5 for VI, and then the 1.5 for VF, and then I'm solving for P. And I get 5 atm. Did the pressure go up? Like we expected, it did. It went up from 1.5 up to 5. Let's look at the next equation. Charles' law. So with Charles' law, we are looking at volume and temperature. So what is the relationship between volume and temperature? Well, volume and temperature in Charles' law are actually proportional. So what that means is if one goes up, the other goes up. So if we increase the temperature, we're going to be increasing the volume, and that's what this picture here is showing, right? The flame increased, meaning the temperature increased, making the gas increase as well, the volume of the gas. So a good example of this is my son's birthday party. His birthday is in August. It's very hot outside, right? High temperatures. So we got some helium balloons for his birthday party, but the birthday party was outdoors. Well, we filled up those helium balloons inside at a low temperature. Okay, so they had a certain volume at that low temperature. When we brought those balloons outside, what happened is they popped. They exploded. Why did they explode? Because we increased the temperature. When we increased that temperature, the volume of those balloons also increased. It increased to the point that the balloon could not hold its form and they popped. Another example using that proportionality between temperature and volume in Charles' law is if you took a balloon and you put it in ice water. Okay. They've also done, if you've ever been to the Museum of Discovery, they do this example with liquid nitrogen, which is very, very cold. So if you take a balloon and you put it in cold water, what happens is the balloon shrinks because the temperature now went down, so the volume of the balloon is also going to go down because volume and temperature are proportional to each other, so they're going to go in the same direction. When you remove that balloon from the cold water, it's going to re-expand because the temperature is now going up, so the volume is going to go back up. Utilizing Charles' law. So here's an example calculation where Charles' law would apply. So we have a balloon filled with helium, and we have a certain volume in liters and a certain temperature. The question is then asking you to solve for the volume if we increase the temperature to 50. So one thing I want to point out, the first step you always want to take when approaching these word problems is to look at the units given to you and convert if necessary. Now we want to convert that degrees Celsius to Kelvin. So you'll notice on your conversion sheet or on your equation sheet for chapter 5 that I have the conversion factor to convert from Celsius to Kelvin. We did this in chapter 1. And all you need to do to convert from Celsius to Kelvin is add 273. So make sure you do those conversions before you make that list of knowns and unknowns. Then rearrange the equation accordingly to solve for the unknown. I have a YouTube video posted working through several of these problems in chapter 5, showing you how to rearrange equations, because that's really the hardest part, is just rearranging the equation to solve for the unknown variable. Once you rearrange the equation, you just plug in the numbers and solve. Next, we're going to look at the combined gas law. And what the combined gas law is, it's including pressure and volume, but also temperature. Okay, so all three variables are included now. So for these types of problems, you are going to be given 5 of the variables, and you have to solve for the 6th missing variable. Okay, so it's also going to require some rearranging. So I have some examples down here which I do work through on the video. I just want to point out how you'd recognize that these are for the combined gas law. So we have a volume, we have 2 temperatures, and we have a pressure. Okay, so we have 2 temperatures, we have a pressure that's the same on both sides, and we also have a volume. And it's asking us to solve for a volume as well. The second problem, we have 2 volumes, right? Liters, liters. 2 temperatures, or not 2 temperatures, sorry, 1 temperature, and then 2 pressures. Okay, so since this word problem has pressure, volume, and temperature, that would lead you to the combined gas law equation. Avogadro's law. Now I know after chapter 4 you were kind of hoping he would disappear, but he did not. He is making a comeback. So with Avogadro's law, we are going to be using moles, since Avogadro's number defines what a mole is. So for moles, we are using the variable n. So that's what this n sub I and n sub f are. That's the molar amounts, the initial moles and the final moles. We're going to be comparing moles to volume. So the more moles you have of a gas, the higher the volume is going to be. Okay, so they're proportional to each other. Because if you think about it, moles, how many moles you have determines how many atoms of gas are present. right? So if you have more atoms, you're going to need a larger volume to occupy those added extra atoms. Okay, so the more moles, the more atoms. The more atoms, the higher the volume. Here's an example using Avogadro's number. It shouldn't say number, sorry, it should say equation, Avogadro's law. So in this problem, we have 2 molar amounts, and we have 1 volume amount, and they're asking us to solve for the missing volume. So you'll rearrange the equation to solve for V sub F, final volume, and then plug in the numbers. And I show how to work through that problem step by step in the videos. Molar volume of a gas. So what is molar volume? It's the volume occupied by 1 mole of gas at standard temperature pressure. So recognize this STP. What's STP? Standard temperature and pressure. Some of the problems that you're going to be solving will simply say at STP conditions. So when they use those words in a word problem, STP conditions, they are giving you the temperature, and they are also giving you the pressure. So at standard temperature and pressure conditions, the temperature is 273 Kelvin, and the pressure is 1 atm. So if you see those letters, STP, you have been given the temperature and you have been given the pressure. Given these conditions, STP conditions, the volume for any 1 mole of gas is going to be 22.4 liters. So once again, standard temperature and pressure, 273 Kelvin. So the reason I'm pointing out the Kelvin one and not the degrees Celsius is because when we use these equations, we want the temperature to be in Kelvin, not in degrees Celsius. Standard pressure is 1 atm. And if you are talking about 1 mole of gas, that 1 mole of gas at standard temperature and pressure will be equal to 22.4 liters. So the ideal gas law is the second to last equation we're going to talk about. And it's a little different than Boyle's law, Charles' law, combined gas law, because there's no initial and final. With the ideal gas law, you are given 1 pressure, 1 volume, 1 temperature, 1 molar amount. Okay, so that's how, when you're reading these word problems, you'll know when to use the ideal gas law, because you're not given 2 of anything. You're not given 2 pressures. You're not given 2 volumes. Whereas Charles' law, Boyle's law, ideal gas law, you are given 2. Okay. So for this equation, we are going to have the pressure in atm, the volume in liters, just like with all the other equations. N, remember, is the variable for moles, and we still want the temperature in Kelvin. Now, this equation's a little different because we have an R value, and what the R value is a gas constant. So this R value is going to be plugged in for that variable every time you calculate the equation. So when you're using the ideal gas law, you need to insert 0.08206 in for R when you solve. Some gas law examples. So the first one, calculating the number of moles. So you're solving for N in the ideal gas law. How do I know that I'm using the ideal gas law? Because I was given 1 volume, 1 temperature, which notice needs to be converted into Kelvin before you use the equation, and 1 pressure. The next problem, reading it, it's asking you to solve for volume for V, and it looks like all it gives you is the moles. Well, you need way more than that, right? You need temperature, you need pressure. But it does give you the temperature and pressure because it's saying at STP. And remember, STP is standard temperature and pressure conditions. and that means your temperature is 273 Kelvin and your pressure is 1 atm. Now the last equation we're going to talk about, mixtures of gases, partial pressures, Dalton's law of partial pressures. So far the problems we've been encountering, we're talking about one gas, helium or nitrogen or neon. So what Dalton's law of partial pressures is if you have more than one gas present. And if you have more than one gas present, the total pressure is the sum of each pressure that each gas exerts. Okay, so really we're just going to be adding the partial pressures of all the gases present in the mixture to figure out the total pressure. So let's look at that equation. So I said the total pressure is just the sum of all the partial pressures of all the gases present in the mixture. Now notice in this equation we have a dot, dot, dot. The reason for this is because this equation can be applied whether you have 2 gases present or even if you have 10 gases present. If you did have 10 gases present, you would just have a P1, a P2, a P3, a P4, all the way up to P10. Down here I have an example. So the air that we are breathing, if I wanted to figure out the total pressure, I would need to add the partial pressures of all gases in the air. So we're breathing in oxygen, but we're also breathing in nitrogen. We're breathing in a little bit of carbon dioxide, and I'm sure lots of other gases in the air. So if I wanted to figure out the total pressure, I could add the partial pressures of all gases present. So gases and chemical reactions. In chapter 4, we looked at stoichiometry. And what stoichiometry is, where we can convert between moles of one gas into moles of another gas. Okay, so we can use this, take it a step further, and apply it to balanced chemical reactions. We're not going to be doing a lot of these calculations. Okay, that was going to stay in chapter 4. But I do want to show you that it can be applied here, because we will look at this relationship in lab 11, the gas lab. It's not necessarily going to be on an exam, but it's going to be in the lab. So I do want to mention it and show you this relationship for when we get to that lab. So an example of using stoichiometry and relating it to these gas laws. So say I have a question that asks, how many moles of NH3 are formed when I react 2.5 liters of hydrogen under these conditions? So under this temperature and at this pressure. Okay, so in order to do stoichiometry, we need a balanced chemical equation. Once we have a balanced chemical equation, we can use the coefficients as the molar amounts. Do a mole ratio to figure it out. So in order to use the mole ratio, though, I need moles, right? So that's why this first problem is asking how many moles, because I can't use the mole ratio, the coefficients in the reaction equation, unless I have moles. So the first step is to solve for moles. In order to do that, we're going to use the ideal gas law, rearrange it to solve for moles. Okay, so here's my conversion factors. My first equation is the ideal gas law. We're going to rearrange it to solve for N. Once I have N, my moles, I can then use a conversion factor to get between moles of NH3 and then moles of hydrogen. So that's what this conversion factor here is. It is that coefficient of 3 that's in front of hydrogen, and then the coefficient of 2 in front of NH3 to get a mole ratio conversion factor. So let's take it step by step and start by solving for moles. When I rearrange the ideal gas law to solve for moles, I get N is equal to PV divided by RT. From there, I simply plug in the numbers given to me in the original problem. So my pressure was 1.32 atm, My volume was 2.5 liters. I have that R value, that constant, given to me on the equation sheet, and then multiply that by my temperature in the denominator. Plugging those numbers in, I get 0.1055 moles of H2. Okay, so now I have moles of H2. Once I have moles, I can then use my mole ratio conversion factor to get between moles of H2 and moles of NH3, which is what the question is asking for. So I take my moles of H2, and then my conversion factor, which is for every 3 moles of H2, I would produce 2 moles of NH3. I put the 3 on the bottom so that moles of H2 and moles of H2 cancel. And then I put the 2 on the top because that represents my moles of NH3. Calculating that out, I get 0.070 moles of NH3. So this is how we can use the gas laws we just learned and apply stoichiometry to it to get between moles of one gas and moles of another. So we'll be exploring this more in Lab 11. So the last slide is going to look a little bit at liquids and solids, and you'll notice the majority of the chapter focused on gases. So with liquids, solids, and intermolecular forces. So when we talked about intermolecular forces in chapter 4, we were looking at forces between molecules themselves. So the forces between one water molecule and another water molecule. Okay, in the example shown, these forces are represented by little red dots. So this is showing hydrogen bonding. So interactions between a hydrogen on one water molecule and the oxygen on a different water molecule. Okay, so the reason that water has such a high boiling point is because of these forces, because of these attractive forces between them.